Now we know how to increase the sample rate and how to decrease the sample rate. What if we want to just change the sample rate? So we're going to do it by increasing it first and then decreasing it. That's the basic approach. So there we are. We increase the sample rate using the upsampler that we developed, and then we decrease it using the downsampler that we developed. I should, just for completeness, note that the gain of the first one needs to be L, and the gain of the second one will be 1. Now, one of the things that you might notice right away is, what's the point in doing both low-pass filters if they're right after each other? If they're ideal, only the lowest frequency one matters. So we can replace this with the low-pass filter where omega c is equal to the minimum of pi over L and pi over M. And of course we keep the gain at L. So where might you do this? Well, for example, maybe you have a signal with a sample rate of 32 kilohertz and you would like a sample rate of 20 kilohertz. Fs is equal to 32 kilohertz. I'm going to have to do something about the way that fit on the screen. There we are. And we would like it to be 20. So Fs prime equal to 20 kilohertz. And we could get to this by noting that 20 over 32 is equal to 5 over 8. And so we upsample. L is equal to 5 by a factor of 5, and we downsample by a factor of 8. And we get to our new output. Okay, that's the basic approach. Now if you wanted to do something like 44.1 kilohertz, which is the rate for CD audio, and you wanted to convert it to, say, 48 kilohertz, which is the rate for digital audio tapes or recordings, or 96 kilohertz, which is also another digital recording standard, then you end up with some factors that are a lot bigger. And the problem with that is that as you upsample by a factor of L, you are now dealing with this huge data rate. For example, if we upsampled 32 kilohertz by a factor of 5, now we're dealing with 160 kilohertz data rate that we're filtering on. We run some low-pass filters and then we knock the rate back down, but we did all the hard work at the high rate, and that's not very much fun. There's got to be a better way around this. So let's explore one other idea that will lead to more efficient filters. There's no way we can get around going up and then down. We have our low-pass filter in here, and then we go back down. But what could we do? Well, first let's look at what's going on here, see if we can get some intuition. At this point, right in here, it's got to be one of the ugliest arrowheads I've done, and that's really saying something. Let's try that. Okay, we first have a signal coming in that, say, maybe 1, 2, 3, 3, 2, something like that. There's our input signal. So what does the signal look like here? The signal there is 1, 0, 0, 2, 0, 0, 3, 0, 0, and so on. So we've got a bunch of zeros in here. That's the whole point. Now I'm just indulging myself, making little circles. And so this was x0, and now this one is x1, and x2, and so on. So, our intuition tells us that at the input of this filter, we've got a signal that's mostly zeros. So we might be able to save on computation. We don't really need to add up what's going on with all those zero terms. So let's try something different. Instead, we will essentially just get the, well, actually, I'm not quite ready to explain that yet. We have to bring one other thing into account first. And let's call this signal here S of n, just so we have something to refer to. When we've calculated S of n, as soon as we're done calculating it, we're going to be throwing away a lot of samples. In our example, we would have had 4 zeros in between every sample at the input, and then we would have gone to a lot of work to compute a lot of samples, and then we get rid of 7 out of every 8 samples at the output. We just get rid of them. Why are we calculating them in the first place? This seems to be kind of a waste. Okay, now let's see if we can create a picture for what's going on here. Okay, to see how this can be done a little bit more efficiently, let's consider that our low-pass filter is kind of an approximation of a sinc function. And so on. Okay, so we're going to be throwing away most of the samples. So what impact is this going to have on our overall filter operation? First, you can guess that we don't need to calculate every output sample if we're not going to use every output sample. Another thing to consider is that most of the input samples are going to be 0. So let's look at how this might work out. I'm going to line up these two plots right here, and assume that we're doing something like a convolution operation. So for the first sample that's going to be output, we'll have that point, that point, that point, this one, this one, this one. Well, I haven't drawn it out that far. Obviously this one and this one are going to contribute to the output. Those are the only ones contributing to the output because all the rest are being multiplied by 0. Now, if we were to delay one sample, everything's going to shift. And so at that point, this, 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 and those, for some reason my cursor stopped working, contribute to the output, and none others. And finally, at the next sample, the output will only be a function of these filter coefficients. When we get to yet our next sample at the output, then that sample will once again be a function of the yellow filter coefficients. So in other words, at time n, we will use the yellow filters. And actually it's time n plus L times K. Use yellow filter coefficients. and at time n plus lk plus 1, use green filter coefficients, and so on. Okay, now that we have we've kind of divided up our input filter into the parts that are needed for each output sample, we can compute S of n directly from X by using a clever little structure. And in that, we essentially collect all of the yellow coefficients into one box, all the magenta into the next, and then all of the green into the next. And when I say collect, they're put in order. So we now have a shorter filter that would be taken, for example, by just stacking or putting the yellow ones in sequence in the yellow box, and the magenta ones in sequence into the magenta box, and the green ones in sequence into the green box. So now the first output sample will come from here, and then the next output sample will come from there, and finally the third output will come from here. At that point, we start over again back to the first one. So we have okay, and then we have this structure that just rotates between grabbing the samples from each one of those outputs to give us our signal S of n. Grabbing the yellow one, the magenta, green, and then starting over with yellow, magenta, green, and so on and so forth. So that gives us S of n. After that, we throw away half the samples, or more. We throw away m minus 1 out of every mth sample. So you could imagine there are some clever ways to maybe cause this to happen. For example, if m was equal to 2, we could just move our commutator 2 steps each time. So we would grab the yellow, then we'd grab the green, then we'd grab the magenta, and so on and so forth. But as m increases, there are also further efficiencies that can be derived with a little bit more work. But that's the general idea. So here, we will now essentially move this by m steps each time. And we have shorter filters that we're operating on, and we end up now operating at a much slower computation rate. And in fact, polyphase filtering can be extremely efficient, and even more efficient than, say, using simple IIR filters. Plus you have the advantage that you can have FIR filters, which can have linear phase and nicely designed characteristics. We'll be talking more about that later.